another problem. So let me share my screen. And choose the right layout. And now let's see what's the problem about today. Okay, choose layout, set timer. This is the reminder for myself. Starting now. Okay, so you're given n balloons. Index from 0. Signature. Each balloon is painted with a number on it, represented by an array nums. So nums is array list of integers. You are asked to burst all of the balloons. If you burst the ith balloon, you will get some amount of coins that is dependent on numbers on the left and numbers on the right. Okay, return the maximum coins you can collect by bursting the balloons wisely. Wow. So I don't know how to approach this problem yet. Let's just create some test cases. So n balloons painted a number on it. Can the number be negative? And okay, no, it cannot be negative. It can only be 0. So okay, let's maybe start by creating something 2, 1, 3, and figure out what will be the correct answer here. So we need to burst 3 balloons, right? So if we burst this balloon, we get 1 multiplied by 2 multiplied by 3. So it will be 6. And then we need to burst, like there will be 2, 3 left. So how do I track this? So 6 and 2, 3 left. Then if we burst, let's say 2. I'm thinking here it might be relevant which one to burst first, right? So if we burst 2, we will be multiplying 1 by 2 by 3. So it will be 6 again. So 6 plus 6 is 12, and 3 is left. Or if we burst 3, it will be also 3 times 2 times 1, and also 12, but 2 left. So here we only can burst this balloon 3, and we will be adding 3. But here we can only burst 2, and we will be adding 2. So basically this branching gives us that here we will get 15 in the end, and here we will get 14 in the end. And we now see that we should be bursting smaller balloons first, but obviously this is a greedy rule, and this is not the whole rule. There will be some sequence. But let's see, what if we have started by bursting this 2 balloon here? So it would branch here. So let's say we burst 2, and then it will be 2, and 1 and 3 are left. So here we can burst either 1, and then it will be 1 times 1 times 3, so 3, so 5, and only 3 is left. Or we can burst 3, and then it will be also 3 times 1 times 1. So 5, and only 1 is left. But here we will again see that we'll be adding 3, so it will be 8. And here we will be adding 1, so it will be 6. Again, so far the basic greedy rule works, so we should be first bursting the smallest balloon. I think I start to get a sense of it, but let's first figure out what happens if there is 3 here. If we start by bursting 3 here. So if we start by bursting 3, it will be 3 times 1 times 1, so it will be 3. And we will be left with 2 and 1. And then we can be bursting either of those. So let's see, we burst 2. Then it will be 3 plus 2, 5. And only 1 is left. Or we can be bursting 1, so it will be 4, and only 2 is left. So here we will be getting 6 in the end, and here we will also be getting 6 in the end. So we are getting similar numbers for these directions, but obviously bursting 1 first is better. In general, it's clear that we need to use big numbers as many times as possible to multiply by them. So it's kind of clear that you shouldn't burst 3 preliminary, because you can, for example, burst 1, and then it will be using 3 in multiplication, and afterwards you will be bursting 2, and it will also be using 3 in multiplication, and then you will be bursting 3 itself, and it will be using this biggest possible multiplier. So the longer you hold the numbers, the better. But then the problem becomes, okay, so how to choose? This is a greedy rule that we haven't proved that is correct. So we cannot just choose always the smallest available number, and okay, we might be able to choose the smallest available number and burst it, but it feels like this is not the correct answer. This is just intuition right now. I don't know if that's correct or not. But I also cannot prove that you should be only bursting the smaller number first. So one of the things that I'm worried about is corner cases and also zeros. So how do we need to, the corner cases, I mean, what if we burst numbers on the edges of the array and multiply everything by 1? This is one thing, and zeros is another thing. So zeros and of array are something that I want to look at. I think for zeros, the same pattern kind of holds. That doesn't though. So for zeros, we want to multiply it as few times as possible. So does it change anything? I don't see so far that it changes anything in the general greedy rule that we have discussed. Then ends of the array. Let's maybe look at a few more examples just to see how things work. Also, another thing, ordering of equal values. So is it important which one do you remove first? So let's say we have something like 1, 3, 2, 1. Okay, so if we remove this one first, yes, it's better because we will be multiplying by this 3 and this 2 more times if we first remove these ones. Cool. Does it matter which one do we remove first? Doesn't look like it. It's not impacting anything, but it's just one scenario. So I'm thinking that in this case, okay, so here the correct answer is 15. Here the correct answer is 3 plus 2 plus 6 plus 3. So 11 plus 3, 14. Let's maybe try to prove the greedy rule now. So let's say we have an array and A and B numbers. And I'm already not proving much because we also need to prove that there are further ends in the array that are not impacting anything here. But yes, let's assume that those ends of the array are not impacting anything, and we are only choosing between two numbers, A and B, and which we need to burst first. So if A is bigger than B, then if we burst A first, we will just multiply by it once among these two numbers. But if we burst B first, we'll multiply by the bigger number twice. So it's always better to burst start with a smaller number to burst. Okay, this makes sense. Now, does it matter what happens in the ends of the array? I am not sure yet. Okay, how can I prove that this holds always and there is always like this ordering of the balloons that you need to first burst the smaller ones and then burst the bigger ones? Okay, let's say we have an array of A, B, F, whatever, like some sequence of numbers. The final sum we will get by multiplying triplets of these elements of this array. So there is the total amount of multiplications will be the number of the elements. So let's say there are n total elements. Then, oh yeah, it's not only better to I'm thinking whether it's also important to start farther from the edges to choose the smaller number there first. But the thing is that we are never rearranging the balloons, so it doesn't matter. It just matters that we should always burst the smaller balloons first. Okay, so we have n multiplications in total, and it means that there will be n triplets, and the only way to increase it as much as possible is to make each those triplets as big as possible. That means that the bigger numbers should be multiplied more times than the smaller numbers. Yeah, I feel like there is some corner case that I'm not thinking through right now, but I don't know about this. Let's just talk about the implementation and what can be the implementation here. The most straightforward thing that comes to mind is to have a min heap with pointers to, like with values in pointers to this array represented as a doubly linked list. So it will be O of n for representing it as a doubly linked list. Then bursting any element will be essentially O of one operation. And yes, bursting, rearranging things will be O of one operation, and it will be of log n to always retrieve numbers from the min heap. So we will need to burst n balloons, and we will need to heapify things, but heapifying is O of n. Okay, so let's do it step by step. First, we heapify values with pointers to doubly linked list nodes. Then we pop heap to find the smallest value and remove the corresponding node. So once we do that, we just continue doing that until we remove everything from the heap. So popping from the heap is O of log n, and removing the corresponding node is O of 1, and we do it n times, once for each node, and heapifying is basically O of n. So given that we do it n times, overall it will be O of n log n runtime for this algorithm, and O of n space. Okay, implementation. I still haven't proved that I still haven't proved like clearly that this greedy rule is the correct one. I just proposed a hand-wavy intuition. I don't know how to prove it, unfortunately. So let's now just try to implement the solution. Okay, so here we need to create a double linked list, and I need to define another class, which is node. Previous and next both equal to none. I'm also thinking whether I can do it in some simpler way, for example with ordered dictionary or something, but I don't think that in ordered dictionary I can find the key and find two keys next to it. Let's assume that we cannot do that. So and yeah, I forgot that value. Self value equals value, self previous equals previous, self next equals next. So this will be our doubly linked list, and head will be node of 1, and tail will be node of 1, and head next will be tail, and tail previous will be head. Okay, now we have created our doubly linked list, and we need to create nodes for each of our elements in the array. So what do we need to do here? For element in nums, node equals previous will be head. In this case, we will be adding those to the before the tail. So node will be node, and yes, we also need to track this everything in the dictionary. So value, oh no, index to node equals dictionary, and here we need to do for I element in enumerate nums. We will be finding those by indices in this array, because they will be not duplicated. So node will be node of element, maybe let's call it num. Node will be node of num, and node previous will be previous, node next will be tail, previous next will be node, and previous will be node itself. So we are just adding all those nodes to the tail, but that's not it. That's not everything that we need to do here. We also need to add to the index, or we can do it separately. Let's also create heap, which is a list, and heap. I just want to do everything, to add everything, append everything for now, and then I will heapify it in one go. So heap append, what are we appending? We are appending value, which is num, and we are appending index, which is I. Okay. Now heap q, heapify, heap, this is done. And then index to node, yes, we can also do it here, equals node. Okay, so this is all the preliminary work that we need to do. Now, while heap and total equals 0. So while heap q, heap pop, heap, so index, we don't need value, right? We just need index. We are popping our heap for that. Then node will be index to node I, total will be plus or equals to, okay, node previous value times node value times node next value. We will always have previous and next because we have created those dummy nodes for head and tail here that have values of 1. So then we need to do what? Node previous next equals node next, node next previous equals node previous. So we are removing this node and delete node, and not only delete node, like first delete index node I and delete a node, just to be careful with our memory because we don't need those objects anymore. We are removing those. So we are just removing everything and then we are returning total. Okay, how much time do I have left? I don't have left any time. How much time have I spent so far? 26 minutes. So I need to check that everything is correct. So let's go with this simple scenario for now. Okay, so head and tail. Let me just represent it as head and tail. Let me also check that head next is tail, tail previous is head, and both of them have values, and their previous and next are none by default, right? Yes. Okay. So now we are creating heap and we're creating index to node. Previous equals head. So currently previous is pointing to head. And here we are going over numbers. So we start with 2, we create num of 2. Then let's see what happens. First, node previous equals previous. So 2 becomes inserted here and the previous is pointing in this direction. Then previous next is equal to node, so they're connected both ways. Now node next is equal to tail, so we are connecting one way. And the thing that I have forgotten, tail previous is equal to node. So now they're connected in both directions. Okay, 4 connections, that's right, something that we are expecting. And previous becomes node, so instead of h it becomes 2. And now we are also appending heap to heap, and we are appending 2 at index 0, which is good. And we are, that's not what I wanted to do. I wanted to say 2 with index 0. And index to node, I'm saying that index 0 is pointing at node of 2. Okay, so far looks good. Now we are adding 3 and everything is being added to the tail, right? So previous is now, instead of head, it's 2. And yeah, we are appending 1 and we're appending 3 and then tail. So this is our structure, and heap becomes this. So 1 at index 1, 2 at index 0, and then 3 at index 2. So then we are popping things and we are multiplying. We are finding the node based on the index. So we are popping and index is the first. not 0, but the first element. This is correct. We are finding the correct node, and we are adding all these values together. So then we are updating those two connections, and we are removing the node, and we are removing the pointer to this node based on the index, and we are returning total. Okay, it looks reasonable. Let's see how it goes. Okay, wrong answer. Yeah, so I'm clearly missing something here. Let's see what is the example. So first we are bursting 1. Oh, yeah. So it is a corner case against borders. So basically multiplying 1 times 3 times 5 will get us a worse result than multiplying 3 times 5 times 8. And this is actually reasonable because if we remove 5 here, we will the 3 will be multiplied. Instead of multiplying by 1 times 5, it will be multiplied by 8. So yeah, well, our greedy rule is incorrect, as I suspected. Unfortunately, I wasn't able to figure this out, and creating those additional tests that I didn't think about. I just had intuition that this is incorrect. What can you do? I don't know. I guess that's it for today. I will offline figure out what went wrong, and we'll think about it more. But thank you, everyone, if anyone is watching this, and see you tomorrow.